What we've been talking about thus far is using the first derivative to find critical values, and then from critical values going into finding critical points. We are going to use the second derivative along with the first derivative to help us with the identification of points to determine if they're max, if they're min, if they're inflection points. And it's important to know what a particular location is, because you don't want to be minimizing your profit or have your production set up at what's an inflection point instead of a maximum or a minimum point. Okay, so we're going to continue taking a look at some additional information to allow you to make a decision on what's going on. Now, one of the things that you got to be careful of, okay, think about the dashboard on your car. On your car, you've got a gauge that goes 10, 20, 30, 40. I know it goes faster than this. I'm hoping, unless you got a very old VW Bug, 60. And that's the speedometer, isn't it? You also have a gauge up there that goes E, F, and you've got a needle somewhere in between there. What's the E and the F? You better know that or you shouldn't be driving. That's fuel gauge, isn't it? Okay, so you got one for fuel. Then you have either what's termed an idiot light or a gauge marked C and H, and somewhere in there is where that one usually rides, and that's the engine temperature. Okay, if you don't have a gauge for temperature and it's just a light that comes on that says check engine or something like that, or it says engine temp, if that light ever comes on, man, get off the road fast, because it means your engine's about to cook. I don't know if you know that or not. Okay, and by cook, that means it's about to expand to the point where the parts can't move anymore and there's enough friction to actually rub and weld together. That's expensive. That's called new engine time. Okay, so anyway, what does this have to do with calculus? There are several other gauges on your dashboard as well. Okay. Each of these tells you something very different about the condition or the state of the vehicle, doesn't it? Okay. And if you get mixed up what the gauges are telling you, you've got a problem. People will mix up f of x, f prime of x, and f double prime of x. Mixing these three up, as far as what they're telling you, can be every bit as problematic as mixing up those three gauges up there. And what you say by mixing up the gauges makes every bit as much sense as saying, but officer, I couldn't have been speeding. I've got a full tank of gas. Can you imagine the roll of the eyes you're going to get on a statement like that? Okay? But you got to be careful, because just like these gauges on your instrument panel tell you very different things, and if you reference one when you should be talking about something else, it sounds every bit as foolish to mix up f, f prime, and f double prime. It's very important to keep in mind that what f is going to give you is y values. What f prime is going to give you, I'm hoping at this point, everybody is getting sick of hearing it, is slopes. And the second derivative is going to give you concavity. Each of these is important. Each of these tells you something very, very different about the function. Mixing them up makes every bit as much sense as the comment, I couldn't have been speeding, I've got a full tank of gas. They have nothing to do with each other, do they? Okay? And it would probably give the officer pause to wonder why you're even behind the wheel of a car. Okay. Our original function tells us what's actually going on. The original function is going to model whatever the situation is that we're trying to describe, whether it be production, temperatures, total sales, whatever it might be. the concentration of a medicine in the blood system. Okay? The original function, f of x, tells you what the concentration, the sales, the temperature, whatever is going to be at the next point in time, or whatever might be our independent variable. The derivative tells you how is that temperature changing, how are sales changing, okay? How is the concentration of the medicine in the bloodstream changing? So the original function tells you where you are. The derivative tells you in what direction and how fast is it changing. The second derivative tells you, are we in an area where the change is increasing? It's getting faster. And if the change is increasing or getting faster, that means the slopes are going up. Is the change decreasing, which would mean the function's leveling out? Just knowing the first derivative is not adequate to decide how things are going, because those two curves that I have drawn there are both increasing functions, aren't they? Which of those two would you rather have your projected sales look like for your company? Or does it really make any difference? They're both the same. They're telling you very different things, aren't they? Sales are both increasing. In both of those, the sales are going up. However, in this one, it's time to start thinking about your product or what your next product needs to be, or something or other, because in the graph that I just drew the arrow to, sales there are leveling off. Whereas in the other one, sales are picking up. Two very different things to have sales picking up versus sales leveling off. Very different decisions made on how the company is going to be managed, how many people you're going to hire, how much equipment you're going to be looking at. Do we need to look at renting, leasing, buying new facilities? Based all on the second derivative, the concavity. Okay? So as we move into chapter 3, section 2, we're going to have all three of these things. You're going to have the function, you're going to have the first derivative, you're going to have the second derivative. Be sure that you always keep them labeled. Okay, f equals f prime equals f double prime equals. Okay, I mentioned the other day that personally I always put the function, the derivative, and the second derivative into y1, y2, and y3 respectively on your calculator. There are going to come times where you've got to know what is the y value, what's the slope there, and what's the concavity. And it's handy to have all three functions in. That way, as you reference the table, boom, you've got all three values sitting right there in front of you. So you can read the entire dashboard. Okay? Okay. So, what are we after in this? Being able to locate and classify relative extremes using the second derivative test. I realized that the other day we were working with situations where, and I'm making up numbers here, 3, 1, and 5. If f prime of -4 is greater than 0 and f prime of 0 is less than 0, and f prime of 2 is greater than 0, and then f prime of 7 is less than 0. The other day we discussed this information can help us to identify what x equals -3, 1, and 5 are. In this first case, we go from increasing to decreasing. Here we have increasing, here we have decreasing. If we go from increasing to decreasing, what we have there is a relative max. If we go from decreasing to increasing, what we have there is a relative min. And then if we go from increasing to decreasing, we have once again a relative maximum. You can speculate as to whether it's a max or a min based on the first derivative information. Okay? That's one way to identify maxes and mins. There is a second way to classify the maxes and mins, or the inflection points, and that's using the second derivative test. The advantage to knowing information with the second derivative is it gives you two different ways to figure out what's going on. In some cases, it'll be easier or more advantageous to use the first derivative. In other cases, it'll be more advantageous to use the second derivative. We're going to want to pull up both things so that we can figure out which we want to use. Okay. The second thing is we're going to want to be able to determine concavity on, remember we talked about this a while back on proving continuity? This stuff works on continuous functions. So we've got to be able to determine continuity before we can do any of this stuff. Just like with the first derivative, you cannot always figure out what the first derivative is at a particular location until you can determine if it is continuous at that value of x. This continuity stuff is going to keep up all year long. Next semester when we get into integration, if it's not continuous, you got problems. Okay, first thing, if you have a function whose first derivative exists on an open interval I, that doesn't mean it has to exist everywhere. It may just be that it exists between some value a and some value b. So if the first derivative exists, okay, and the first derivative is always positive. In other words, it's getting bigger as you move from here to here to here. As you draw those various tangent lines, the slope's getting bigger. Now, getting bigger can look like moving from -7 to -5. That's moving in a positive direction. Doesn't say it is positive, but it's moving in the positive direction because you're going from -7 to -5, and that's moving in the direction of positive values. Okay? If it is positive over the whole interval, it's concave up. Now, concave up is going to be greater than 0 or less than 0. Let's see, concave up is smiling, and you're smiling if things are going positive or negative? Oh yeah, positive. So this is going to be positive here. Okay, concave up, positive. Similarly, if the slope is decreasing, that means getting smaller. It goes from 3 to 1 to 0 to -2. That's moving in a negative direction. Okay? If the slopes are decreasing, what you have on that interval is something that is concave down. You can tell it's concave down if the second derivative is less than 0. Now, the nice thing about the second derivative for determining concavity is we can do it with the first derivative. Okay? We could look at what's the slope here, what's the slope here, what's the slope here, what's the slope here, and then after evaluating the first derivative at 4 points, look at the direction the slope is moving, look at the pattern, and decide, aha, this means that it's going in a negative direction, it must be concave down. But you got to evaluate the function at 4 different points now, don't you? Whereas if you have the second derivative, you put in any one of these points, any one of them will result in the second derivative being negative, and boom, you're done. Instead of having to do it 4 times, you do it once. And boom, you're done. So it's more efficient with the second derivative. Efficient's going to be important. Okay? When you get a career type job, they're going to ask a couple of things of you. 1, be there on time. 2, treat the customers well. 3, get your work done accurately and quickly. Those 4 things, and you'll be promoted right on up the ladder. That's all it takes to be a successful worker. Okay? If you can do it with a second derivative, and boom, you've got it done in 1 step, as opposed to having to do 4 or 5 and looking for patterns and this and that, and you get the point. The second derivative is a much more efficient way to determine if something's concave up or down, and in determining if it's concave up or down, you can also tell if it's a maximum or a minimum. Okay? If it's concave up, as we've talked about before, you're at a minimum point. If it's concave down, as we've talked about before, you're at a maximum point. Okay? This basically just reiterates in the form of a theorem what we've already talked about with concavity. If the second derivative is positive, the graph is concave up. Second derivative is negative, the graph is concave down. Okay? Now, throw in another theorem. These theorems are important. They're the rules of the game. Okay? Just like in hockey. If you come skating along and the ref blows the whistle and you're, well, what? I didn't touch anybody. I was just skating down the ice. And the ref says, you were offsides. And you say, what's offsides mean? I wasn't touching anybody. You were offsides. Cough up the puck. But dude, I didn't do anything. Yes, you did. If you don't know the rules, are you going to be successful? Not very likely. Okay? One of the rules says that if the second derivative is positive, you are at a minimum. If the second derivative is negative, you are at a maximum. That shouldn't be any surprise. I've been trying to toss that out there for weeks now, so that when we got to Theorem 5 on the second derivative test for relative extremes, it wouldn't be any surprise to you. It'd be, yeah, I've been hearing that for weeks. No big deal there. Okay? So you need to be aware that this really is one of the rules of the game. Okay, so with that all in hand, let's go about working with a couple of functions here. We're going to do 3 or 4 of them. We're going to look at graphing them. We're going to find maxes. We're going to find mins. We're going to find inflection points. These are all important values to be able to locate and to be able to differentiate one from the other without seeing a graph. Because ultimately where we're headed, and we'll be there in January, is graphs can't even be drawn anymore. And that's the way it works in the real world a lot of times. There are too many parts, there are too many products, there's too much stuff involved to be able to graph it because you've now got 16, 18, 50 variables. You can't graph with 18 variables. Okay? One of the classes we used to offer here, I really enjoyed teaching. By the end of the semester, we'd be working with 70 and 80 variables. Can you graph something in 80 dimensions? There's no way. But they still had to find the maximum points and the minimum points and know which was which. Okay? These rules are what get you there, even though you can't see a picture. Okay, so if we're going to graph this, determine where the relative maxima are. Relative maxima is a fancy way of saying the high and the low points. In the business world or elsewhere, it's usually called optimize. And optimize can be make it as big as possible, make it as little as possible. Well, how do I know which they want? Depends on the context. If we're talking about revenue and profit, you want to make it what? Big. If you're talking about cost, waste, total miles driven, you want to make it small. Okay? Please don't ever let those words slide out of your mouth. Chuck, do you want me to make this profit function big or little? Because my comment will be, if I was your boss, you would be fired. Okay? What are you doing working here if you don't even know the basics? True? Should we be making a profit or should we be losing money here? Duck when you ask that question. Somebody's going to throw something at you. Okay? So realize that if it says optimize, and I will intentionally put that word on quizzes and tests and things because folks out in the real world are always going to be saying, okay, now we're working with the profit. Remember, we want to maximize the profit. That's a given, dude. Right? Okay? So be careful. Look at the context, and you can answer for yourself, are we looking for maxes or mins? Okay, However, in this one, we don't know if this is a max or a min. This is just a practice problem. We're going to find both, identify which of their maxes and which of their mins, and just use this as a practice. We're going to be moving into actual applications here in a little bit being a couple of days, and you'll longingly look back on the good old days here where the function was already given to you. Okay, so we've got this. You know the steps up to this point. Step 1. Compute the derivative. F prime of x, hey, this is pretty easy on this one. It's 3x squared, 6x minus 9. Remember when that used to be the whole problem? Compute the derivative. And that was it. And you'd spend 5 minutes on this. Step 2. Let's stay on the same slide. Step 2. Is going to be set the derivative equal to 0 and solve. That means we've got our 3x squared plus 6x minus 9 equals 0. In this case, we can divide by 3. If you have the quadratic formula already programmed on your calculator, should you bother dividing by 3 or just pop this into the quadratic formula? Pop it in. You don't have to deal with dividing by 3. That just burns up time. How do we know we can use the quadratic formula on this? Because it's a quadratic. It's x squared and it's equal to 0. Some of your chuckle remember to get over to the math lab and get the quadratic formula on. I'm going to divide by 3. This is going to give us plus 2x minus 3 equals 0. In this case, this is going to factor into x plus 3, x minus 1 equals 0. This gives us x is equal to a negative 3 or a positive 1. Those are important. Those are called the, what are those called? Critical value. Yeah, the critical numbers. Nick's going to play it safe. Okay, the critical values. Why aren't these the critical points? Don't have any y values. Oh, that's right. The next thing we could do here, and I'm going to label these as critical values so I don't get them mixed up. Next thing I'm going to do here is I'm going to compute the critical points. Now, the critical points are going to have an x value of negative 3 something or other, or 1 something or other. How do I get the critical points? He's rooting around in his backpack. I guess that must mean it's time for the calculator. Okay? To get the critical points, I'm going to go to y equals, I'm going to clear out whatever's in there. I'm going to put in x raised to the third plus 3x squared, subtract 9x, subtract 13. Then I'm going to go to the table and clear out what's there. And I'm going to plug in negative 3, enter, 1, enter. Aha! And this is going to be 14, negative 18. Everybody good with that? Now, while I'm at it, I'm going to go y equals, and in y2, I'm going to put 3x squared plus 6x, subtract 9. When you put your derivative in, be sure it's before you've divided by 3. Otherwise, your values won't come out right when it comes time to put them into the table. Okay? Everybody good there? So what we've done on step 2 is to set the derivative equal to 0. We've determined what the critical values are. From that, we got the critical points. Everybody's good so far? Then what I'm going to do are a couple things. Step 3, here comes a new one for us. I'm going to compute the second derivative and set it equal to 0. Well, the second derivative is going to be 6x plus 6 equals 0, which means x is negative 1. Now, you've got to be careful. the first derivative equals 0 means where are the slopes 0? The slope is going to be 0 at one of 3 points. The slope could be 0 didn't want that. Well, it's going to insist on it. It can be 0 up here. It can be 0 down here. Or your graph can do some funky thing like this, where it's an inflection point and it can be 0 there. Does that make sense to everybody? So the first derivative equal to 0 can turn up max points, min points, or inflection points. The second derivative equal to 0. Now remember what second derivative does. It talks about concavity. If you go from concave up, second derivative positive, to concave down, second derivative negative. If you're going from positive to negative, what do you have to drive through to get from positive to negative? 0, don't you? If you're going from concave down to concave up, you're going from negative to positive, and once again you have to drive through 0. When the second derivative is 0, this will turn up inflection points. Does that make sense to you? Okay. So we can have an inflection point at -1, comma, oops, I got to go back to my table. And let's see, I'm going to put in -1, enter. Aha, I get -2. Now this is where things can get tricky, because not only do I have my function x cubed in the table, but I also have the derivative, the x squared stuff showing up on the table. But I know what's what, because y1 on my calculator is always used for a y value. y2 is always used for the slope. And guess what y3 is going to be? Concavity. Aha. I'm going to put that in quick like. Okay, so that's going to be 6x plus 6. There we go. So I have all three of them in now. Okay. If you take a look, and I'll show it here on my calculator. See if this will project. On the calculator, it's kind of an ancient looking display for the word weight, isn't it? If you take a look on the calculator, you can see it. I have there, under y1, the original function. Aha, maybe that'll make it a little more legible. Okay, under y2, the derivative, and under y3, the second derivative. Which makes it kind of nice, because then when I go to the table, my y1 values, oh look, there are all the y values to get my points. At -3, 1, and -1. At y2, that's slopes. Does it make sense that at -3, the slope is 0? At +1, the slope is 0. Is that a surprise to you? At those two locations, the slope is 0. Shouldn't, because that's where we set the first derivative equal to 0. The slope better be 0 there. Does that make sense? The slope at the third point, not 0, so it's not leveling out there. Now, using the arrow, the right arrow to move over, and now do you see it gives us y3? Now this is kind of cool, because this is really helpful information here. What we also have for step 4, and I know you can't see what I'm writing just yet, but what we have on the calculator is the second derivative at -3 is -12. The second derivative evaluated at 1 is a +12. Do you see that? It's right there on the table. Okay. Now, if I go back to the slides, you can see over in the lower right-hand area here, I wrote step 4. The second derivative at -3 is a negative value. That tells you right away that the critical point, -314, is a what? Max or min? Well, let's see. It's negative, so that means it's concave down. And if it's negative, you have a maximum. I'm going to put down relative maximum because we don't know if it's the absolute maximum for the whole deal or not. The second derivative at +1, which is the point 1, -18, has a positive second derivative. That means it's concave up, which means at that location we have a relative minimum. Does that make sense? So in fairly short order, you can go through, click off a whole checklist of stuff, find your maxes, find your mins, locate your inflection points. Okay? With that information, you can go ahead and sketch a graph of this, couldn't you? Well, let's see here. Do this in the upper right corner where we have a little space. At the point -3, 1, 2, 3, we're going to be up 14. I'll just put it up here somewhere. And there would be 15, 10, 5. Over at 1, we're going to be down 18, so there's 5, 10, 15, 20. So we're going to be down about there. And we have an inflection point at -1, -2, so right about there. We also know something about the point -314. At -314, is this thing concave up or concave down? Well, it's negative, so it's concave down. Which means in this area, the graph is concave down. Does that make sense how I sketched that in? When we turn our attentions to x equals 1, we get a second derivative that's positive, which means in that area it's concave up. Well, concave up is going to look more like that. Can you connect those pieces and make a graph out of that? Yeah, you can. Fairly easily. Make sure it goes through the... Wow, it just went crazy on that, didn't it? Make sure it sort of goes through your inflection point. Up, down. The only thing left to do with this is to label the points. Negative, or I'm sorry, it's a positive 1. The negative's on the 18. Our inflection point is going to be -1, -2. And our maximum point here is going to be at -3, +14. And that's got it done. It is entirely possible to have a maximum value where the x value is negative. How could that be? If we're working with a chemical process. Okay? Different chemical processes have reactions that occur best at different temperatures. It might be that the highest reaction rate is at a -3 degrees centigrade. Now remember, -3 degrees centigrade is probably about 29 degrees Fahrenheit. Does that make sense to everybody? How to quick whip through that? There's one more thing I'm going to throw in on the next example that we just ran out of room for here. And what that's going to be is creating a number line. Remember how we did this with the first derivative stuff? We put our -3, we put our +1. Does that look familiar to you? We're also going to throw in the second derivative information, -1. So what we're going to do is we're going to look at labeling things like here the first derivative is, here the first derivative is, and then down below we're going to label information about the second derivative, and by compiling the information between the first and second derivative, you know exactly what the shape of the graph is on any particular interval. Make sense? So we're on vacation, trying to get there. I look down at the speedometer, 70 miles an hour. I look at the fuel tank, it says F. Are we good to roll? Yep, sounds good to me. Wait, Dad, we got to use the restroom. No, we just stopped 10 minutes ago, but it's been 10 minutes. Okay? It happens when you got a carload of people. Okay. So, all kinds of stuff here. Aha, we do have, okay, we'll just do this on the next one. I forgot that I slid that in there. There's the graph. Does that make sense to you? Pretty straightforward on the graph. Okay, what I'm going to do here, looking at the time, we got about 15 minutes. And we've got about 4 different examples here, but we don't have time to work through 4 of them. I want to go after... Let's try this one. See how this works. There we go. Okay. Okay, so let's see what's going on with this one. See where we are with this. Find the relative max-mins on 1 plus 8x squared minus x to the 4th sketch the graph. As before, we're going to click through the same steps. Chapter 3 is kind of nice in this respect because it's always the same steps. Roll in a different function, same steps. They all get treated the same. So step 1 is going to be compute the derivative. And you can look at this. It's 16x minus 4x cubed. That's the easy part, isn't it? That was the calculus. That was easy. Step 2, what's step 2? Well, take this derivative and set it equal to 0. That means that we're going to have now, because we're down to just a few minutes here, I'm going to kind of combine some things. Look at the 16x and the 4x cubed. Do you see they both have a common factor of 4x? I'm going to factor that out as I write this down. So it's going to be 4x times 4 minus x squared. Equals 0. This gives us 3 separate values. Notice I did not divide by 4x. If I would have divided by 4x, that x would be gone now, wouldn't it? We would still get 2 solutions. We would get the solution x equals plus or minus 2, but we would miss out on the solution x equals 0. If you divide by x, you're going to lose one of your solutions. And it'll always be that you lose x equals 0. And you don't want to be throwing that away because that may be your best option. Okay, well, let's see. We have some critical values. And those critical values are x equals -2, 0, +2, which means we have some critical points. And those critical points are going to be -2, comma, something or other, 0, comma, something or other, and +2, comma, something or other. Quick way to get these. Fire up that calculator, press y equals, clear out whatever's in there from the last round. I'm going to put in 1 plus 8x squared, subtract x to the 4th. Press enter. Into y2, I'm going to put 16x subtract 4x raised to the 3rd. Now, while I'm here, should I go ahead and poke in the second derivative? Might as well. I mean, you can look at it and figure out what the second derivative is. It's going to be 16 subtract 12x squared. Boom, all three are in. Now, when I go to the table, I'm going to put in my x values, which are -2, 0, and +2. Looking in the y1 column, at x equals -2, the y value is 17. At x equals 0, the y value is 1. And at x equals +2, the y value is a positive 17. Is everybody good with that? So that's pretty quick, isn't it? Okay, so we got that done. We're moving right along. Let's move to step 3, which is going to be compute the second derivative. Well, we've already done that. That's going to be 16 minus 12x squared, and that's already in your calculator, isn't it? So if we evaluate our second derivative at -2, evaluate our second derivative at 0, and evaluate, I think we can slide this in, the second derivative at +2. Wait a minute, these values are already on your calculator, aren't they? Should be. I'm going to move over to the y3 column, and whoa, look at there. At x equals -2, the second derivative is -32. At x equals 0, the second derivative is 16 and -32. Now this gives you some information about these critical points. What's it tell you? What's x equals -2? Is that a max, min? It's a maximum. Okay, so it's going to be a relative maximum. X equals 0 is going to be a relative minimum, isn't it? X equals -32 is going to be a relative maximum. We're flying through this stuff, aren't we? This doesn't take much time at all. Next thing, step 4. We're going to locate our inflection points. Well, our inflection points occur where the second derivative equals 0. That means we're going to have 16 minus 2x squared equals 0, or 16 equals 2x squared, or we get our x squared equals 8. Ooh, that's ugly. X equals plus or minus the square root of 8. That's got to be wrong, Chuck. It's not an integer. Welcome to the real world. Did I make a mistake? Where did I mess up? Oh. Welcome to the real world. Mistakes happen. Thank you. Well, that's going to make this even uglier. Okay, so we're going to have 16 over 12. Thank you very much. So we're going to have 4 over 3, which is going to give us plus or minus the square root of 4/3, which you can write as the square root of 4 over the square root of 3. And is it very polite to leave square roots in the denominator? Is that considered kind of, that's kind of a social faux pas, right? So we're going to do a square root of 3, a square root of 3. So this is going to give us x is equal to plus or minus the square root of 12 over 3, which eventually settles in to be 2 square root of 3 over 3. Whoa. That was the most work we've done so far, and it was all algebra. Calculus was easy. Just getting the 1 in there in front of the 2. How many different inflection points do we have here? 2 of them. Our inflection points are going to be at -2 square root of 3 over 3, comma, something or other, and a +2 square root of 3 over 3, comma, something or other. Now, be careful here. Be really careful. This second value that we're looking for in each of these two is a y value, a slope, or concavity. At this point, we're looking for y values, aren't we? So we can put points on the graph. Does that make sense? These are inflection points. A point has an x value and a y value. And the reason I'm going into so much discussion on this is when we go to the calculator and we go shopping for a number, we've got a couple of issues to deal with here. First, when we go to the table, I get back down over here to x. I'm in the x column. How on earth am I going to put that in? Well, it's going to be parentheses 2 square root of 3 divided by, oops, I need another parentheses there. Now I can do divided by 3 equals. Then I'm going to put parentheses -2 square root of 3, need 2 parentheses, divided by 3 equals. We got to be careful. Remember, we're looking for y values. Is that going to mean referencing y1, y2, or y3? y1, way to go. Okay? So when we pull out these x values, it's going to be 9.89 for both of them. Okay, so we've got all kinds of stuff going on here. We have some critical points. We have some inflection points. Okay. And I'm going to quick write those down on the chalkboard up here, well, the whiteboard, because where we're headed next is a different slide, and we're going to need these numbers. So we have this -217, 0, 1, +217. Then we have our -2 square root 3 over 3, 9.89. And this is going to be plus or minus that to cover both inflection points. Okay. Okay, so if we go through all this, okay, one of the things I skipped over that I'm assuming that you know, what x values are we allowed to use with this function? In other words, what's the domain of a polynomial? Any number. Any real number will work. Okay? Because we're working with a polynomial. Okay, so we went through all this stuff. Does that look familiar to you? Look at there. We've got x equals 0, x equals 2, x equals -2. Oh, those are our critical points, aren't they? Got those. Hey, look at there. Some stuff about second derivative. Our inflection points, after you folks pointing out, wait a minute, Chuck, you forgot a 1. We got the right inflection points. Now, here is what I want to spend a little bit of time we have left talking about. On a number line, we can put our x values. Here's our -2, 0, +2. Those are the x values for the first derivative. What I'm going to do is, before I go any further, I'm going to talk about this section. So I'm going to look at something like, what is the derivative at negative 3. Well, to get the derivative at negative 3, all I got to do on my calculator is put in 3 and then look under y2. Oh, it's negative. It says negative 60. I don't care that it's negative 60. I just want that it's negative. The next interval we're going to look at is from negative 2 to 0. Okay, so I'm going to put in something like negative 1. This is kind of weird. Less than 0. Okay, between 0 and 2, well, that would be something like the derivative evaluated at a positive 1. There, it's going to be greater than 0. And lastly, I want something to the right of 2. So I'm going to evaluate the derivative at perhaps 3. And that gives me less than 0. With that information, we know what this graph is doing on each of those 4 intervals, don't we? On the leftmost interval, it's decreasing. On the next interval, it's negative, so it is still doing what? Still decreasing on that whole interval. The next interval, it's positive, so it is increasing. And then on the last interval, it is decreasing. Remember the other day I told you to be careful, they do not alternate back and forth between increasing and decreasing in every case. There you go. They're not alternating, are they? The 2 intervals to the left are both decreasing. Next thing is, I'll change the pen color here. Let's do our second derivative. 2 square root of 3 over 3. Let's see. 2 times the square root of 3 divided by 3. Okay, that's about 1.1. Why do I want the 1.1? So I know where these numbers land on the number line. So here, we're going to have something at negative 1.15 and something at positive 1.15. We're interested in what the second derivative is doing on each of these 3 intervals. Okay? So I can go back to my table. So we're probably going to have to finish this up next time, aren't we? And I want a number to the left of negative 1.15. Well, I've already got something up there. Oh, look, I have this negative 2. And if I go to the third derivative, it's less than 0. If I go to 0, it's greater than 0. And if I go to something like to the right of this 1.15, like f of 2, it's less than 0. And that tells you right away where it is concave up and concave down, doesn't it? It shows you what the shape of each piece is. We'll pick up here on Wednesday. You've got enough information to start going after the homework for this section. Practice another one of these, or finish this one up here in class, won't hurt anybody. Okay, folks, I hope you have a good day. I look forward to seeing you all on Wednesday.